Hi, my name is Nolan Trouvet, and for my final project, I chose to map a small concrete statue located on the back side of Anne Arundel Hall, just behind McKeldin Library. My goal for this project was to create a 3D virtual representation of the concrete statue that you can see here. I selected this target due to its concrete structure, which is quite reflective, a major benefit for the line laser used as a transmitter in the LiDAR system that I will describe in detail. I also chose it for its relatively small size and simple geometry, as well as its accessibility on all sides. My LiDAR system consisted of a 3D printed chassis mounted onto an adjustable tripod. Starting from the bottom of the chassis, a line laser served as a transmitter. Just above it, an accelerometer was used to capture the vertical angle of each measurement. Above the breadboard, an Arduino sent the serial data provided by the accelerometer to a Raspberry Pi mounted at the top of the chassis. A camera was interfaced with the Pi to serve as the receiver. Before deploying my LiDAR to map the statue, I calibrated it in my apartment by capturing individual JPEG images of the line laser taken at known distances. I used a color masking technique that will be described later in order to isolate the laser from the rest of the pixels in the camera's frame. With a known separation distance of 12 inches between the line laser and the camera mounted on the chassis, I used a Python script to calculate the laser's distance from the tripod through geometric triangulation based on the red pixel's distance from the center of the camera's frame. I then fitted these experimental distance values to a theoretical curve, ensuring the accuracy of my specific setup. Here you can see me approaching the target from the south side of campus. On our right side is McKeldin Library, and on the left here is Anne Arundel Hall. Just up these steps you can see how much darker it gets, which was a huge help for me in my data collection process. Here I am setting up the field deployable LiDAR. I powered the Arduino through the Raspberry Pi and powered the Pi through a micro USB cable to my computer. I established a virtual VNC connection via Ethernet to interface with the Pi on my laptop. These snapshots represent my initial data collection on the front side of the statue. With my JPEG images now captured, I transfer them over onto my laptop. Here they are, the set for the front side of the statue. My next step is to run a color masking Python script in an attempt to isolate the red line from the rest of the image. In order to do this, I create an HSV range that blacks out all of the pixels that don't fall within the HSV specified values. As you can see now, it is isolated. Now that I have the HSV range, I import it into this Python program. This Python program takes in the JPEG images, masks them using that color range, and then outputs a text file with XYZ coordinates that I can then import into MATLAB. I can then plot these together, and you can see now a visual representation of the front side of the statue. Next, I moved over to the right side of the statue. This real-time video shows you exactly what goes into taking a single JPEG measurement. So I'm adjusting the angle of the tripod to the desired IMU value that I'm reading off the accelerometer and taking an individual picture. I then repeated this process over 20 times on the right side, as you can see from each of these JPEG images. Following the same set of procedures, I captured my JPEG images for the backside of the statue. and again for the final left side of the statue. Notice the significant changes in ambient lighting as I move from one side to the other. I encountered several challenges throughout my data collection process. The first of which dealt with ambient lighting. There was this bright light shining off the brick in the background as I took the pictures of the front side of the statue. In order to get around this and make the color masking easier, I decided to block it with a tarp. Additionally, I had to deal with some uneven ground, as you can see in this picture, which made stabilizing the tripod more difficult. Another challenge was the location of this wooden post that you could see in the center of the frame, which made my access to the back of the statue more difficult than on the other sides. Repeating the previously described process, I imported 4 text files into MATLAB, one for each side of the statue, obtained from the JPEG images. I then filtered out some of the noisy values that I didn't want to show up in my point cloud. This was done through cutoffs based off of the position of each the x, y, z coordinates in the point cloud. This was repeated on all sides. I also use simple trigonometric functions that you can see here to orient each of the sides properly, merging all 4 text files into one complete point cloud. Here is my final rendition of the 3D point cloud of the statue. As you can see, it mimics reality fairly closely. It has a circular top section that protrudes from the base, as well as a hexagonal geometry on the lower section. This becomes especially clear when looking from the top view as well as the bottom view. Here is a further visualization of the final point cloud. I then used MATLAB to write the 4 text files merged in the plot, front, back, left, and right, to a combined text file in preparation for the creation of a 3D mesh. In order to create a 3D mesh of the statue, I first used MeshLab to compute the normals of each point in the imported combined text file. I then applied a Poisson mesh and removed the extra parts of the mesh, as you can see here. The final mesh looks quite similar to the point cloud rendition, as well as the physical statue. Again, the circular section at the top protrudes, and the hexagonal geometry of the base is clearly visible.